the second part of us talking about R. If this needs to go on to next week some, then it'll go on to next week some. Okay? What my hope is that you'll be able to take what I posted online, download the syntax, download the data, and be able to replicate the analysis by running the whole thing. That's my goal. All right? I don't even know the ins and outs of all of R yet myself, so I'm pretty sure I can't teach you all the ins and outs, but I'm not looking to teach you any advanced things in R. It's just get data in, get results. That's going to be enough for us for right now, and if that works, just a working knowledge of it, I'm happy. Okay? So on that note, I see that most of you have the data, and most of you have been able to find the set working directory and run it without error. Correct? I'm going to start talking again. If you need a hand, Susan, would you be willing to see people? And at some point, I'll jump off and we'll both work together. Thank you again for your help. So the next step is all we've done to R is tell it where your data, the folder it's in. And the reason we did that, because now we're going to read our data in. Okay? I'm going to try to make it so that the data come to you in a very uniform format. They will always be in a comma-delimited file. If you haven't worked with a comma-delimited file before, this is what it is. If you open up, this is our file from Lecture 1. If you open it up in a text editor, just something that looks like text, all that means is our data is stored in columns that are separated by commas. And the first row of our data file gives us the header for the variable. So this is one observation per row, and within each comma is each of the variables, ID, sex, height, in inches, and weight in pounds. Right? And each of those map onto the stuff that we've done in lecture before. The reason I use comma files is that if you're in Windows and you have Excel installed, which I think we get for free, right, through our campus, they give you Office. If you just click on it to open it, it opens in Excel. And you can see the data like you would in SPSS. All right, so that's why I use comma files. One click to open, you can see it, so you can see what you're reading in. Okay? So all it is a text file, and R's function to read that is this function called read.csv. So looking at this syntax here, I'm going to store the data in an object named data01. So whenever I want to refer to my data in some other part of syntax, it will always be data01. Okay? Read.csv is the function that does so. And it takes, there are two, what we call, when R, everything is either an object or a function. An object stores data, a function does something. And you can tell it's a function by this open and close parenthesis, right? So when you typed in read clipboard, you had to put open and close parenthesis. It was a function that told you what the clipboard was on your computer, but it didn't need any input to it. It just ran by itself. But R thought of it as a function, so it still needed that open and close parenthesis, even though there was nothing sent to it. Read CSV is a function that needs a little input. It's a function that is built to go and read a comma-delimited file, and you have to tell it two things. First, what's the file name? Right? So in quotes, I put the literal file name MV14 PRE 905 _ lecture 01, and here's the key thing, .csv. Sometimes on your computers it will hide that last part of it for you, the extension. R wants the whole thing. It's still there. Right? The second thing that you have to give it is whether or not the CSV file has the first row representing your variable names. So do you ever input data into SPSS? Had like a little window that would pop through as options. One of the options was, do you have variable names in the first row of your data? That's what header equals true means. The word header followed by equals, followed by true, all in capital letters. And when you see that you put the word true in capital letters, you see how it turns it a shade of blue? That's RStudio telling you that true is something R will be able to read by itself. Right? It's a command. So, a couple other notes on the function itself. The file, all you have to put is the name of the file, because with this code that you ran before, you've set the directory already. Had you not set the directory before, you'd have to give it this whole long string before the file name. And nobody wants to do that now, right? Okay, good. I don't want to do that. That used to drive me crazy. So, can I give you a little comic relief? Or try to? Maybe? So if you go, thank you. Clint? No. Clint, yes. Okay, so if we go to the R blog, which sounds like a pirate, the basic syntax, it actually has help here. And when I started in R, they didn't use the equal sign to put something into an object. It used what looked like an arrow. You see that? Greater than dash. It said, oh, that means x equals y. Or take y and put it into x. And I love how he puts it here. Speaking of which, assignment, which means putting something on the left-hand side of an equals into the thing on the right-hand side, looks stupid. Pardon my French, but I shit you not. These all have the equivalent effect of storing the value b in A. A, arrow B, B arrow A, assign A, B, B equals A, or A equals B. I shit you not. I love how he just puts it out there. Yeah. So, anyway, this is some things that would be nice if you'd like to read kind of what the heck is going on with a little bit of comic relief. This is a place to go. I enjoy it. Otherwise, you'll have to deal with me yammering on. So, read.csv is a function. If we go and run, we could click the run button. I don't like to use the mouse. It slows me down, so I always have keyboard shortcuts, which you can see is Control-Enter. So you can hit that. And now, you'll see it submitted it to the console. I did not get an error, which, like, if you don't get an error, you should be like, yes. Yes?
Okay, so before you hit run, you had your cursor, you can have it anywhere in that line?
Yep, just on the line itself.
Okay.
Yep. Yeah, once you hit run, you'll see it submitted down in the console window. You'll see that line. And then your cursor will need to move down to the next line of syntax, even if it's a comment. Good question. Thank you. Was it? Sorry. Trying to think here. Jamie? Okay, got it. Pardon me. The whole switching around thing is good. It's healthy for me. I'll learn. Okay, so data 01 exists. How many of you were able to do that? All right. Round of applause. This is celebrate your victories when you can get them.
Does anybody have trouble?
Yeah, that's a good question. If you have trouble, we're not going to boo you yet. Just kidding. You can boo me. Actually, if you booed me whenever I screwed up, that would be awesome. That would be cool. At one point, when I taught over in the psych building, I had my students throw stuff at me. I thought it was really cool. I had to dodge stuff as I was teaching. Anyway. Now what you'll see over here is data, right? And here's where it starts to look a little bit like SPSS. Click on data or double click it. Look what you see. It's your data. Do you see data? Woo! You win. That's it, right? There's your data. Getting the data in never felt so hard. And yet, the sense of accomplishment, right? Okay, so you have all four of the variables: ID, sex, height, and weight. And data is a very special type of object in R. It's called a data frame. So R, remember, we can create things that are objects, and objects are any number of things. They can be text, they can be data, right? A data frame contains a bunch of numbers separated by the variable names. So if you wanted to know what was in your data, you can click over here and you'll see it all, right? It's all listed over there. The other thing you can do, which I didn't type up here, but I could just as well, if I put the word names and I create a function, so I open a parenthesis, and I put data 01, what it will tell me is each of the variable names in my object, right? So later on, to do an analysis, you will create another object, right? And that other object will have a bunch of names and each of those names will have your results. Some of it will be like a t-table, or a series of regression slopes. Some of it will be an ANOVA table. There'll be all sorts of goodies that you'll find. But mostly it's comprehensive, I would say. Have you guys, has R left anything out of any of your stuff that you've used before? Anybody? No. Anyway, I'm sure it has. Okay, so you with me? Question? The default is false, and actually, thank you for this question. If you go over to Help, the Help window on the bottom right, and click the Help tab, and type in read.csv, you'll see what the defaults happen to be. And this is about the only thing this is useful for. I'll make this expanded. So it says read.csv, and it's actually this one, read.table, is first. And actually, header should be true by default in read.csv. So anytime you see this, these are all the things that you can put in parentheses in your function. Right? It'll say file, that's your file name. Header, that's whether the first line is. But if you see header equals true, that means it's, if you don't put that in there, it will still run. It will just assume it's true. There's a header row. So to answer your question, header is true by default in read.csv. I put it in. There's nothing wrong to keep it in there just to double check. But then all these other things show up as well. If you want to know what those are, here's where help is unhelpful. Right, Cameron? Go down here. It's supposed to tell you what each of those things are. Generally speaking, I find what I need to use, and I move on. So in my syntax will probably be what you need to use. I will never go and make you find something that I haven't used at first. That doesn't stop you from looking, and if you find something I haven't used, please bring it to my attention. I will learn from you. But that said, that's where this help system comes in handy. Questions? This is starting to make a little bit of sense? Not quite. All right. So this is our data. And now, if you've gotten that far without error, the good news is, if you run everything else in this file, so if you highlight everything else, it will replicate all the analyses from the lecture, or it should at least. So I'm going to hit Control-Shift-End and highlight everything. I'm going to hit the Run button, and what you should see is a bunch of numbers down here in this box. Okay? I'm going to go through some of the syntax. I'll let you kind of match the syntax to lecture when you need it. But I'd like to get to the big picture stuff before I get into the fine-grained minutia. Okay? And on that note about fine-grained minutia versus big picture, this week's homework is due Friday, but I posted next week's homework that Susan thankfully created for you that was based on R, based on something that looks very similar to what we've done already with our first week's class. And pretty much everything that's in this syntax you'll get. And one of those things that you'll have to do, though, is create a variable for male instead of female. Is that right? So R's syntax to do that is right up here. This is our recode for syntax. If you just copy and paste it in, you'll be fine. I will decipher it later for you, but let me tell you, this has been a 12-year struggle for me to get this right, and I had to look this up before I put it in. So on that note, just make a mental note, recoding syntax right up here. Bless you. But what I'm trying to say, what we can do here is if we go to look at the data, I'll give you a little bit of description for this. If we look at the data here, female, our sex variable is coded as an F or an M. Right? And R will need it to be numbers, zeros or ones. Now, as we get a little bit further along, when we get in next week's lecture, I'll show you how to automate that in R. There's a word called factor, which enumerates it for you. But for right now's purposes, we're just going to go forward and say, if sex equals female, I want to give them a 1. Or if sex equals F, put a 1 there. Right? I'm creating a female variable. And that's what this syntax does. Data 01, the dollar sign, and a word afterwards. So that dollar sign says, within our data 01 object, go find the female variable. Right? So for instance, if we're to type that down here, this is one good thing about the console. If I were to give it one good thing, it's great for trial and error, and if you're like me, and error and error and error, and more error. You should have seen me this afternoon in my office. I was a little bit frustrated. If you're working in the building, you probably heard me. I'll try to keep it down next time. But for instance, if I type data 01 $ female, or sex, it lists all of my observations for that variable. The number 1 over here is just kind of an index marker. It goes, and I don't remember how much it puts on there, but when it displays data, if it has to wrap the line, the number that you see in brackets on the left-hand side is the observation number it wrapped at. So if this were to go on another line, you'd see probably 21 here, and it would go, that would be the 21st observation as it goes on and on. So you see, when I put the $sex there, it tells me all the data that's in sex. And so what the syntax does, that you'll copy and paste up here, is it says, I want to create a brand new variable named female. I want it to be in my data 01 data set. And these brackets mean if this thing is true. So what does that mean? If the data in my sex variable of data 01 equals, and the double equals is like an if equals. A single equal says take this and put it over in the other thing. Double equal says is this true? If, right? So if my data has the letter F there, and it's in quotes, so it's a letter, then make my new variable equal to 1. If my data has an M there, make it a 0. There are other commands that you can do to do this. There's an if statement, there's other things, but in this case, I've recoded it for female. Here, I'm going to walk you through next week's homework, Susan. If I'm stealing your thunder, I'm sorry.
Not at all.
Okay. So it's not exactly copy and paste that you'll have to do. You'll have to switch it. We want you to create a variable named male. Okay? So, start out with your name of your data set, data 01. You put a $sign. Oh, whoa. Sorry. Let me back up. Start out with data 01. Put a $sign. Put the name of the new variable, which should be you passing already. 100% tonight. All right? And then, this is the condition. You can just copy this first line. Data 01 $sex equals F. What should it be? 0. Got it? So the next line is similar. Data 01 male, the same thing in brackets, equals 1. Cool? Now you are, what we would say, you're manipulating data. Let me tell you, statistics has some of the worst verbs and adjectives out there for descriptors. Like when we explain variance, people call that variance decomposition. We're decomposing variance. We're manipulating data. No wonder like people make stuff up and they publish it, right? Anyway, how are we doing? Do you think we can sort of make it through? Is it survivable? Maybe? Okay, I'm looking for survivable. We're looking for... So my wife hates it that whenever we go travel, and I never watch TV, but somehow when we'll be like on the road somewhere, and it'll be 10:30 at night, and we'll just be kind of like flipping through the TV channels. I always stop on a show called Survivor Man. Have you ever seen that show? All right, that is awesome. Like it's just like I would probably never watch it otherwise. It's about a guy who just puts himself in harm's way just to show you how to survive. Right? He'll show up. He was in Sweden once, and he was driving his car on a snowy road and purposely got himself stranded to go and find a way to get rescued and so forth. Anyway, ridiculous, right? I want you to be survivor person for R. Okay? I want you to be like, yeah, I'm stranded on a desert island and my homework's due. And all I have is R. All right? If you can do that, you're good. Anyway, never mind. Trying. This other line right here has a whole bunch of stuff to it that I thought was beyond for what we want to talk today, but that would actually accomplish the same thing. We'll get there later. Okay, so how about we start to see some of our data? Now that our data's in, wouldn't you like to see it? Wouldn't that be nice? How about we go and create a scatter plot matrix like we had in the slides? To do that, this function called pairs is needed. So if you put your cursor on that line and run it, whoa, over in the plots box, you'll get the following. A plot that's a scatter plot matrix. This is the syntax I used to put that in lecture. Syntax for it, and believe me, I don't have this stored in memory. I had to look this up. That's a tilde. Sometimes people call that a squiggle. What would you call this little thing right here? Tilde? Okay. Squiggle is what... Maybe I don't work with the most enlightened people. Not Susan. She's bringing me up a notch here, but people from my experience, they like to call things squiggle. No, I'm just kidding. I do too. Female, then you just put the list of things you want together. And then there's a comma, which means the next thing you need to tell it. And this line right here, data equals data 01. Some of the functions in R make it very easy for you because you can tell it, I have a data frame, which is an object that has variables of these names in it. Right? Which is why the line above us, we had to put $female after data 01, and in here we don't. We don't have to put it because we've been able to tell R in this function, look inside this data set. It's got a variable named female. It's got a variable named height. It's got a variable named weight. Does that make sense? Okay. How about a histogram? So this plotting window over here is actually the reason I used R for many, many years. When I was in grad school, I used a markup language called LaTeX to write all my papers and slides and stuff. Anyone ever use LaTeX? All right. It makes nice typesetting. So actually, when you submit papers to journals, they take your paper from Word or whatever software you wrote it in and convert it into actually something called TeX, a harder version of LaTeX, and it paginates it in a way that makes it look nice on the page, right? Problem with that is it doesn't make plots for you, but R's plots were to fit into it, so I always used R for plots. Point being, this window over here isn't like your typical plot window. If you noticed, when I made the window big, it got fuzzy, and then all of a sudden it got real clear, right? And if I were to shrink the window a little bit, you'd see it gets fuzzy, and then it clears up again. That fuzzy to clearness that it does is something called vector drawn. It's a vector drawn graphic, which means whenever it displays the picture, it will display it relative to the size of your screen on your display. Right? So our window here is not very big, but that's one of the more awesome things about it. So when if you wanted to save this graph, you can click Export. You could save it as a PDF, or you could save it as an image. And when you do so, it asks you, what size do you want it to be? And sure enough, if you change the dimensions, like like if I make the height 500, I can update the preview to it. Maybe. Well, anyway, you can rescale it, and it will look just as clear. If you're in some other type of software package, or if you're using internet graphics like a JPEG or a PNG, they don't rescale. Right? It's one of the nice things about it. But this plot window here is rather dynamic. So what R likes to think about it is it essentially gives you access to the entire thing. You can draw pixels if you wanted to on there with syntax. And this next section of code is going to take this window and partition it so that we display two graphs at the same time. So if we want to have things side by side for a comparison, this is where I put the histogram of our data before. And the way this works, the function par, I don't know why it's par, they must like golf, makes that window give you options to fix it. So par mf row, and this C function, what we're going to get used to in the next couple of weeks, says set the plot to show two pictures in one row. So if you hit this button and you draw the two histograms, you'll see them side by side. And they entered in sequentially, that you saw there. Right? And then this last line, par mf row, puts it back to one image overall. This C function actually stands for it's like a list. I think it stands for concatenate to a group. That's the number of pictures per row, and that's the number of pictures per column. It's like making a grid out of it. Right? So it's a 1 by 1 grid. It's just one picture. Above it, a 1 by 2 grid. There's two pictures in one row. How we doing? By the way, there's tons of help online for R. Yes, question?
I tried to run it, and it looks like it ran in the console, but not.
No picture?
No picture.
Does it? Sometimes do you have an arrow over by? Do you have it on plots first of all?
Yes, I have it on plot.
Do you have an arrow by plots?
Yeah, but it's not available, really.
Susan, do you mind helping Jamie real quick? Thank you. Sorry. Thank you. Thank you very much. While she gets that worked on, other questions about the plotting functions? Okay. Any of you excited to use R? Thank you, Clint. All right. So somebody. How many of your other classes use R? You've had a few. What have you been in that used it?
It was actually intermediate stats.
Oh yeah? Was it in
Psych.
Psych? Who was the teacher?
Aaron Bolton.
Okay, cool. What about you?
Testing theory.
Test theory with Billy?
Yeah.
Yeah. Cameron, where did you have it?
IRT and SEM.
IRT and SEM? Great. So I was talking to Billy Skorupski about this as to if I should use R or whatnot. And he said a lot of the 900 level classes he's used R in before, so I'm trying to make it a thing. I'm actually writing more of my software in R, so the class I teach next fall, which is going to be diagnostic models, which are my research area, I'll be using R for doing a lot of the data analysis as well. So hopefully this will transcend a little bit more. I don't know. Did you get, Jamie, did you get all taken care of?
No, I couldn't figure it out.
Well, we'll talk after class or send me an email. We'll get that straightened out, okay? No worries, Susan. Patience for everybody, right? Thank you. So next, I want descriptive statistics of all my variables. There was a slide that had descriptive statistics. This function called summary pretty much works on almost any type of object. This is where the fun of R happens. Sometimes you're doing an analysis and you don't see any data or you don't see any results until you say, oh yeah, show me the summary of that thing, and then it outputs it. So if I tell it summary, now again, I have to tell it the data set here. Why is that? I have to because it does not have a place to put data equals. Right? So I have to give it this whole variable of data all by itself. It's like being in SPSS and having multiple data sets if you've worked with those. But if I submit this code, what you'll see down here is it tells me the following. It tells me, oh shoot, you can't see it very well. There, how about this? Is that a little better? We've got all of our mean, our median, our maximum, our minimum, and so forth for each of those variables. Pretty self-sufficient. Anyone want to guess what var stands for? Variance. So variance, if I type var, what you see here, actually I was looking to figure out how to do this today and I couldn't find it. It made me very frustrated. Evidently I found it the first week. This is a 3x3 covariance matrix. Remember what variance was? Variance is correlation's evil twin. Right? It's correlation with units. Do you remember this from last week? Right? So down the diagonal is the variance of each variable. if on the off diagonal is the covariance between each variable. And how I get it to show all three variables at once is I have to combine them into their own little mini data set using this function called cbind. So for those of you who are new to syntax and programming in general, var is a function, right? It says, you give me data, I give you variance. But what if you wanted more than one variance? We're in multivariate here, right? We want covariances. You have to give it more than one data set. So this cbind thing, if I were just to copy it and paste it, what it does is it takes all three of these variables and just puts it into what we call a matrix. We're going to talk about matrices coming up in a couple weeks, but it's just a box that stores the data. And so when you say R, give me the variance of this thing, it says, oh, you've got three variables. I need to give you the variance and covariance for each of those. Variance of each and the covariance of every pair. Right? So when you see a function that's embedded within a function, you can always unpack them and see what they're doing in the console window. But it's kind of a shorthand way of getting R to work for you pretty quickly. I've tried to make a lot of the syntax not have that in it. I try to keep the shorthand out because it's very hard to read if you've got var and then cbind and then something else in it. But I'm not necessarily so good at it. But I'm going to make a promise that most of the syntax I give you every week will try not to embed functions within functions unless we get to a point where we're comfortable with it. Okay? Questions? Is this coming together a little bit for you? Questions? Sorry, I looked down. Questions? Anybody? Does anyone like Diet Mountain Dew? No. I have not. Becky, aside from snow, what do you like? Sorry. You've been very good about saying you don't like statistics or NBA or Diet Mountain. What's that?
Yeah, I like the dentist.
What do you like?
Diet Mountain Dew is
Poison.
poison.
What should I be drinking instead?
Water.
Oh. If water was so healthy, it would taste good.
Tea.
And maybe if I put some saccharin in it, that'd be awesome. So am I shortening my life expectancy by drinking Diet Dew?
I don't think the research is conclusive, but
I was just wondering though, how many minutes or hours would one can be off of my life?
I know that Mountain Dew is illegal in some countries.
That's
because of
awesome.
some of the content in it.
It's pretty cool. I love being back in Lawrence. No, sorry. Sorry, Becky. I get a sense a lot of people are more into natural things, right? Not Becky. Jamie, you're from here.
Mm-hmm.
Lawrence is your word, right? So it's much more of a healthy place, right?
I don't know.
No?
Depends.
Okay. I was going to say, I think the healthiest place I've been at, the places where I draw the most scorn for drinking this is like Boulder, Colorado. Like everybody there, they have more health food stores per capita than I think they have more Whole Foods than they have regular grocery stores. And everybody rides their bike up to get one. And anyway, sorry. I'm very lucky. I like Boulder quite a bit. I actually really enjoy Boulder. I just haven't caught on to the whole being healthy thing yet. I go in cycles. And now I'm on an unhealthy cycle now, but you watch. In 20 years, maybe I'll be healthy. We'll see. Sorry. I digress. I'm trying to mix life with statistics. So if var made a covariance matrix, correlation matrix would be core. And there you have it. There's our core. See that right there? Now you'll note, when I just, in syntax, when I have a function all by itself, it just puts your stuff, your results, right in the console window, right there. Right? Which is mildly annoying because how do you get that into your paper? Right? You have to copy that stuff over. The other thing that you can do is you could always save anything as an object. So I didn't have it in syntax, but I could have said, I could have made an object named correlation matrix and said it's equal to core. And what would it have done? Not shown me output yet, but it would have saved it up over here. And that's my correlation matrix right up there. All right? Actually, this is actually copy and pastable. This is new to me, too. Look at that. Is that a copy button? Show a new window. Oh. Anyway, point being, saving it as an object allows you to manipulate it in different ways. Yet again, sounding sinister. Okay, how we doing?
Then you also just write CSV or write table?
You can write table. You can write table. It will table it down here, I believe, or you can write table and it will go out to an output window, output file as well. Yeah. So if you wanted to write, what Cameron is saying, in this read.csv package help over here, one thing that it does do well, even if it doesn't give you good help, is at the bottom of it, it tells you C also for things that are related. And one of those here is write.table. So it's the opposite of read, right? If reading brings the data in, writing spits the data back out. So one of the options we could have done with that is to write it to a CSV file or write it to a table. And if I were to do that, I could put the function, here, let me put it in syntax here. Write.csv, we'll make it a CSV file. We need to give it the name of the object, correlation matrix, and file equals mycore.csv. And if we do that, correlation matrix not found, you're kidding me, right? Did I screw up the typing? I did. Helps to spell. There we go. In the folder where I pointed my R thing to, you'll find a new file. And lo and behold, there's your correlations. Thank you, Cameron. So you can always take whatever's in R and spit it out to a file and then copy and paste from there if you wanted to. It's a little bit more takes a little bit more effort, but it does work. Do you have any other questions about this? By the way, I love the interaction. I like the questions. I'm going to get to know each of you this semester, and I'm excited about that. This is why I have a faculty job, because I enjoy working with you. Questions? I'm going to drink my poison. Poison never. So is alcohol poison?
Yes.
Okay. And if someone said, would you like this poison or that poison? Just kidding. I won't go there. Wouldn't choose Diet Mountain Dew. But, you know, if you put it with Southern Comfort, two wrongs make a right. Sorry. Just kidding. Don't answer. Just asking. Okay. So how about we do some analyses now? We were just doing descriptive statistics. That was so stat, whatever you call it, right? Basic statistics ago. We're in a 900 level class now, which was 900 level back at Nebraska as well. But in Georgia, this would have been an 8,000 level class. So talk about differences. Model 01 is going to be an object where I'm going to store the empty model. So the next thing you want to know is, how do I do ANOVA, or how do I do a linear model? The function LM is what we'll be using almost exclusively to start the course. LM stands for linear model. And linear model works like this. You, in parentheses, tell it your linear model. You start out with your dependent variable. So in our case, we were trying to predict weight. Weight LB. You put a tilde. The tilde is the equal sign. Now the empty model has absolutely nothing that's predicting it. But you can't put nothing there, otherwise it chokes. So you need to put the number 1. The number 1, what we'll come to find out in a couple weeks, if we were to do this in linear algebra, the intercept gets predicted. It gets the beta 0. It's like saying it's multiplying a variable that everybody has a 1 for. And that's what that 1 stands for there, right? So weight LB tilde 1 is our empty model. And because we're allowed to put data equals data 01, we don't need to put a $sign and the data set name in front of it. Cool? So all of a sudden we submit this code and, whoops, that was not cool. Remember that movie back when I used to work here almost? Actually, it was a little before that. Dude, where's my car? Dude, where's my model? That was a great movie, right? Anyone see Dude, Where's My Car? Good. Unfortunately. See, that was one of those things where when you're drinking a lot of poison, it'd be a good movie to watch. Always wanted to know what a cabinet full of pudding would look like. The way that you get access to your results is through the word summary. Right? Summary of your model gives you all the following. Let's see if I can make this where we can see it a little bit better. What we have here, it starts with the word call. This is just what formula you use to run the analysis. So it's an R syntax, so it's still kind of problematic. It gives you some, garbage about residuals. We don't want to look at that yet, okay? Just ignore the residuals. But here's where the magic happens. Coefficients. Coefficients are the beta weights, the regression slopes. But in our model, we don't have any. We just have the intercept. And do you remember what the intercept should be for the empty model? The mean of the dependent variable. In fact, we type mean and we put the dependent variable one, data 01 $, weight, cannot spell, LB. Take a look. Our result is 183.4, which is our mean. Awesome, right? So far, so good. The other model parameter happened to be the variance of error, although here they call it the standard error. So that's the square root of the variance. It's the residual standard deviation. So if we were to figure out, if in a perfect world, the variance of error would be this thing squared, so 56.38 caret 2 is 3178.704. What if we put, instead of mean, we put the word var in front? Well, we don't quite get the same matchup, and that's because one's dividing by n and one's divided by n minus 1. But I'll bet if we look at the var function, we can figure that out. Doesn't say. Method. Nope. Anyway, but it's pretty close. Finally, if you want to know the ANOVA table, although the ANOVA table on this thing is pretty lame, it doesn't really tell us much stuff. The syntax for that is the word ANOVA. So if we submit that, we see the following ANOVA table. It doesn't even have a table. It's got like just the residual. This is the ANOVA table line for error. Do you remember the ANOVA table had degrees of freedom, sums of squares, right? Mean square, which was sums of squares divided by degrees of freedom. This thing here is our mean square error. Actually, that matches. Look at that. Right there. That matches our variance. That's true. And so forth. Questions about this? Do you think you can replicate this so far? Have a fighting chance, maybe? Survivor person style? Like it's better than being in, where was he before? Somewhere in South Africa on the coast. South America, excuse me. I don't know. Anyway, so model 2 is where we added in height. So instead of a 1 afterwards, we put height. Seems pretty self-evident. So let's run that real quick. Model 2, there is our statistics, intercept, height, coefficient. That is our slope. This is the model 2 that we ran before. You have the standard error there. These statistics it tells you here is for the overall model. So if you have a bunch of predictors here, this F statistic is your omnibus test, saying whether or not one of those regression slopes is different from 0. Remember that omnibus thing? No? Yeah, simultaneous test of all the slopes all at once, although here there's just one of them. It's significant. This is your overall model, multiple R squared, or if you worry about sample size stuff, the adjusted R squared is listed there as well. The ANOVA table for this will also give you a similar result, but it tells you the F value, which is actually this T value squared in this case. but not always. So wait for next week for why. And actually, not always is true of all stat packages. It's just one of those weird quirks that I want to express to you in just a little bit. Questions on this? Feeling confident? I like it. Even if you're not super confident, let me tell you, you can do it. I'm confident in your ability. So, what about model comparisons? Remember the R-squared change test? If you want it to do it for you, you don't have to look up the R-squared. You don't have to go look up the R-squared or the error variance or all that stuff you had to do before. You just use our friend the ANOVA function, and you put in both models as arguments. Take a look at what it does. Did it do it? There it goes. Oh, stop it, Templin. You can tell it's the end of the day. I'm just really sharp, aren't I? Do you see how this works here on this ANOVA table? This is model 1. There's weight LB with just the intercept. Model 2, it's got height. Take a look at that right there. It's your R-squared change test. That's awesome. You don't have to write any extra code. You don't have to do anything else. Like in SAS, you have to go figure this stuff out by hand. Or you'd have to go write a macro or something. Here, it's one line of code. That's one place R is quicker than SAS. Not always, but one place. Did they have one of those options in SPSS? I'm sure they did, didn't they? I don't know. The thing is, I've got SPSS here, but it doesn't work. Like if I start it up, it'll tell me your license is expired. And that's how I feign ignorance. I don't know SPSS. Just kidding. There it is, right there. Your license renewal date has passed. Oh, no, it still works. This product will stop working if a new license isn't installed soon. Well, I'd like to use you, but I can't even close you, so, you know. Anyway, go away. How are we doing? All right, let's add the other predictors real quick.
So wait, so that last one, that just tells you whether your change R-squared is significant?
That's right. It tells you essentially, if you have a nested model here, it tells you what your additional variable would be in terms of change in R-square, or if you will, reduction in sums of squares error for it. There's a lot of ways of describing it, but essentially it's that same old formula that talks about how big your sums of squared error was in one model and versus the other one, whether or not that was by chance or not. When we get to linear models with maximum likelihood, our sums of squares goes away. But we have a similar statistic called the likelihood ratio test, and wouldn't you know it, the ANOVA function knows how to do that too. So we will always use this, at least I'm assuming, maybe don't quote me on this completely, I gotta go lighten it up, I'm not an R expert either. But I'm pretty sure when we do ANOVA, it will tell us which model is preferred. What this is saying here is because the p-value is significant, that's saying that the R-squared change by adding the variable height is significantly different from 0. Or the beta weight is bigger than 0. Different ways of looking at it. We can also mean center our data. That's the next line of code here. Now, what I'm doing is creating a brand new data variable in our data set. Right? So whenever you see data $01 $, and I have a new name here, that new name is just the original variable of height in inches minus the mean of height in inches. Right? So if I put that in the data, and actually if I highlight this whole thing right here, you'll see what it looks like. My data frame, in my console window. So here, first observation was negative 11.9. That means the first person's height was 11.9 inches below the average. Do you see how it wraps? The 12th person's observation is 0.01. That means person 12 is 1/10 of an inch taller than the average. Make sense for the most part? Excellent. By the way, one thing about the console I didn't tell you, if you want to go to the previous commands that you've typed, and this works in the Windows console and also the Linux console, and I'm pretty sure it works in the Mac's Unix console, if you hit up, the up arrow at the bottom, it will cycle through your history of your previous commands. And you can go to them again or modify them. It's a quick, kind of a quick. But if you get in the middle of it and you don't want that one, you can always hit escape and it goes away. Furthermore, you can see your history of commands up in the history window in the top right as well, and you can highlight a command, and you can send it to the console, for instance, where you can tell it to execute. So RStudio makes it a little bit more accessible for working with. Okay, the remainder of the assignment, the remainder of work of this analysis was built on the series of models. And pretty much the only thing different about the code as we go on is how do we add multiple predictors. And when we get to Model 4, you'll see that. Model 4 had height that was mean-centered, that was in inches, and female, both as main effects, without the interaction. So the plus sign is what you use there, right? All the terms that you want as main effects by themselves with the plus is your code for that. If you want the interaction, so I'll just run this real quick. Here's the analysis itself. You can see all of the results. This should match up with what we had done. Here's our ANOVA table from the analysis for each of those. Now finally, if we go down to Model 5, we added the interaction. And the syntax to add the interaction was literally taking female and putting a star and then putting height in, height inches mean-centered. It takes both of the main effect variable names, and that star means multiply them together. And if you remember in our lecture slides, which I, of course, closed, I'm going to pull them back out again here. That one. Go to where I left off. Model 5, do you see beta 3? It's our interaction coefficient, and it's multiplying the height variable times the female variable. The syntax in R replicates that perfectly, right? You have height variable times female variable. So when we put that in to our analysis, we have Model 5. We have our summary of that with all of our statistics. We have our ANOVA table. And, well, if you had the R syntax and the data from homework, you could just do that and see which one was significant. Or you could tell by your significant effect right here. This is your R squared change test. The neat thing about the R squared change test, you see this is your ANOVA table. And the ANOVA table for the interaction had the p-value that was 7.065 times e to the negative 06. That means take the decimal point and put it out 6 spaces. Really, really tiny, right? That aligns perfectly with the p-value that comes from the R squared change test, right? It's doing the same thing. So it's one of the neat things. Questions? How are we doing? Okay, couple more things. And we'll call it a night. R, one of the things that people like the most about R is that it has a bunch of these statistics that are built in out of off the shelf, fresh off the internet, right? The download that you get. But if you want to go and use more elaborate statistics, it works like your Mac does, or your iPad does, or your Android phone does, in that there's an app for that. All right? Although R doesn't call it an app, R calls a series of new functions a package. So if you look at the top here, if you go to your Tools window here, and you go to Install Packages, you may get a question as to which repository to come from. But in this box here that says Packages, you can type package name. So for instance, next week we're going to use one called multcomp. And it tells us, multcomp, oh, you want the multcomp package. Okay, I want to install that and its dependencies. So you click Install, and R will connect to the internet. Oh, it's not up there. There it goes. And it literally downloads the package for you and installs it for you. Now there's one, if the package itself, this multcomp package actually refers to several other packages which it installs as well. And when it's all done with that, they're all on your machine. Now you can't necessarily use it, so we'll sometimes have the word library. You put the word library or the function library and you put the word in quotes multcomp. And what you'll see is it will load that library. And now you'll have a set of new functions that you can't exactly see where it is, but if you were to go search help for, didn't have it there. There we go. So one of the multcomp packages is GLHT, General Linear Hypotheses. We're going to use GLHT, General Linear Hypothesis Testing, to do inferential statistics based on our linear models next week. And in my syntax, what you'll see online next week, it's already posted. If I go to the website, maybe. Right here, next week's class, simple marginal interaction effects. The R syntax for it, at the top, has this automating packages needed for analysis at the top. So again, I've tried to make it set up to automatically download and install multcomp for you when you go and download this file. And then later on, when we get down to where we want to be, we're going to use this GLHT function to give us some results that will help us dissect our analyses a little bit better. This is one of the things that's built in SAS. If you use SAS, there's a proc GLM, which is General Linear Model. And they have a series of things called estimate statements that take your beta weights and recombine them into things. And that's where a lot of statistics comes from. In fact, all your F-tests are nonlinear combinations of your betas and the standard errors for them. So we're going to cover that in the next couple of weeks because, as you would guess, multivariate statistics, everything I say here applies. It's just what they say about PhD piled higher and deeper or something like that. It's just more and more and more and more. So, let's see. Have I forgotten anything, Susan? Would you say something, Susan, that I've forgotten, or would you like to talk about with your use in R?
Well, I don't know, in the homework there's a couple of things that we haven't gone over, but
That would be good.
Probably my fault for adding them.
No, it is not your fault.
I didn't know if you wanted us to let them sort of play around and explore.
No, I'm happy you added them in, and again, there's no fault.
All right.
Thank you for doing the homework. The homework document here. Standard deviation, is that one of them? No?
No, it's the predict. So you got to predict your values. Using the model, you got to get the predicted values.
Okay. That is going to be part of the object,
Okay.
right?
Well, that's not how I did it, but that's a good way to do it.
So she's asking you for predicted values. Remember how you find out what's in an object? Names. Actually, or you highlight it over here if you want to click on it. In environment, like model 01, here's all the stuff in it. It's a whole lot of stuff. Oh my goodness. But if you type names and you put in the function model, let's say 05, it's got coefficients, residuals, and so forth, fitted values, that's predicted.
Oh, perfect.
So you can find it as part of the object built in. How would you get it to tell you the predicted values? You type model 05, I heard it, $, fitted dot values. And these are all the predicted values for every one of your observations. Sorry, Susan, is that what you wanted?
Yeah, that's perfect. I just did
Boom.
it differently, but there's 100 ways.
There are 100 ways to do it. And this is the thing about it. You will tell me things I have no clue about. So this is one of the fun things about it, for me at least. So, hey, by the way, this is the other thing about these R. This is where it gets also better. It has lots of hidden things for you. Wouldn't you like a plot of that model or like to see what happens? If you type the word plot, model 05, it tells you, oh, wait, look, hold on a second. It's trying to give you plots. Residuals versus fitted values. Do you ever remember, did you ever do any diagnostics, model diagnostics in your regression or ANOVA class with residuals? A little bit. One of the things you wanted was that the fitted values and residuals had basically no correlation. This tells you outliers, potentially. This plot over here, have you ever done a QQ plot before? Or a PP plot? Quantile it stands for. What it does is it takes your data, in this case the residuals. What is the assumption about the residuals in a linear model? Normally distributed. Exactly. How do we check if they're normally distributed? What QQ plot does is it says, hey, if they're normally distributed, they should be roughly on this dotted line right here. And if they're not, they'll be far off. And how it does that is it orders your residuals from lowest to highest on their standardized values, and then says, okay, when I had 20 observations in the data set, if I were to observe 20 observations from this normal distribution, the lowest one should have a normal z-score of of this value. The second lowest one should have a z-score right here, and so forth. So it tries to pair up the z-scores, the theoretical quantiles, with that of your residuals. And this, although it's hard to tell with 20 observations, is roughly normal. That's what we wanted it to be. That QQ thing, by the way, is how you check for any distribution. How do you know if something's chi-square? You order your stuff, your data, your stuff. Order your stuff, that sounds like you're on Amazon. Order your data from lowest to highest and go figure out, well, the computer will figure out what a theoretical distribution's lowest and highest values will be, and it'll plot it for you. And R draws a line. Anyway, there are more plots. It'll tell you scale versus location. This is our essentially trying to tell us whether or not our residuals are, and here's the beautiful word from it, homoscedastic. Remember what homoscedastic is? Homogeneity of variance. So we made an assumption about the residuals. We said they were normally distributed. Do you remember what the mean of that normal distribution should have been? 0. You know what the variance was? Sigma squared. Right? But there was only one variance, which meant every one of these observations, residuals, should have been roughly the same variance. And what this plot tries to do is put all the predicted values along with how far off you are. And if you see a kind of a shape to this plot, it's almost like a Rorschach test where you're looking for shapes that are hard to decide, you'll start to see more variability. But what this is saying is, if you look at the kind of the scatter of dots, there's roughly the same amount of variance the whole way through, which is what we would say homogeneity of variance, or another way of putting it is homoscedasticity. You can tell I've been teaching for almost 10 years now with that. This is my 9th year teaching grad school. So finally, did you ever talk about residuals or leverage in linear models? You ever heard about that before? Leverage. What does leverage make you think about? Physics, maybe? Better yet, good position in negotiating. Both of those are true. What leverage means, if you think about it from a physics analogy, I was once stranded in New Mexico. I drove from Sacramento. I was trying to get to the Midwest. I was about 19. I was 18 years old, actually. I was driving a car that had 3 cylinders. But I drove that car close to 125 miles per hour in the desert until it almost fall apart. So I used to like to drive really fast. Now I drive the speed limit. I'm good. And I blew the speed rating of my tire, and it blew out. And I was about 40 miles from Albuquerque. There's a little Geo Metro, which is a little tiny thing. And it had a tie rod that was like this big, right? So I had no leverage to get the lug nuts off of my tire, to take my tire off, put the spare on, right? Sure enough, there was a trucker who took mercy on me, who came in, saw this 18-year-old punk. Back then I was actually I didn't drink the diet stuff. I was healthy. I was like this scrawny little kid, couldn't do it, and he brings out his trucker-sized tire iron, right, that has like like 2 dimensions, and he's like, first thing you're going to do is buy yourself one of these, son. Yes, sir. And that's leverage, right? Well, the same thing happens in linear models. A residual or an outline value can leverage your linear model, your line. Right? So you can have one observation that's so far away from the line that just like putting pressure on that, the tire, the lug nut or whatever, it takes the line and brings it up closer to it rather than the other things. And that's what this plot tries to do. It tries to talk about where your leverage is, your standardized residuals versus how far or how much leverage they're putting on the line itself. So all of these things are kind of esoteric, but they're ways of looking at your results to believe them or not. I remember the first poster I ever presented was significant, and that was because there was one outlier. You take that outlier out, and it completely changed. And that was actually in Albuquerque. So there you have it. Okay. I'm worn out. You ready to quit? Do you have any questions for me? Thank you for your patience. Susan has office hours tomorrow afternoon, and I will have them Thursday afternoon. And you're welcome to make appointments with either or both of us.